So thanks for joining us today. My name is Peter Pouliot, and we're here today to talk to you about SUSE Virtualization and Rancher Prime and the support for Ampere and Arm64 based architectures. So my name is Peter Pouliot. I've been at Ampere almost 6 years. I actually spent 9 years working for SUSE back in the Novell days. I was part of the team that put Linux on Hyper-V, working on virtualization and all those things. And yeah, I live in Massachusetts, and yeah, I'm very passionate about private cloud technologies, virtualization, and infrastructure.
I'm Alejandro Bonilla. I'm a domain solution architect. I actually live here in Jacksonville, Florida. So it was a short ride for me. Glad SUSECon was here. I'll talk mostly about the SUSE virtualization part. Well, Peter is probably just going to focus a little more on the very important aspects of the hardware.
So, one of the things we're going to talk about, obviously, we introduce ourselves. I'm going to introduce you to Ampere. So just a quick question. Does everybody in the room know who Ampere is? Okay, good. I guess we'll learn some stuff today. And then we'll go into SUSE Virtualization Rancher Prime and the state of Arm64 support, and give you an idea of what some Ampere platforms look like. And then Alejandro's going to show it all work. So Ampere Computing is the first modern processor company. So we basically, about 8 years ago, decided, a group of our, well, basically Renee James, she basically decided, she left Intel and decided she wanted to start the next generation processor company that was focused on designing processors for the cloud, right? So part of that was, and if we look at data centers today, we have a lot of real estate with not a lot of stuff in it, right? We have to deal with the power constraints, the cooling constraints of the current chip architectures that exist, what we like to call legacy processor architectures, right? Which historically were designed for the enterprise, right? So what Ampere has done is taken a different approach, and we've focused at the beginning, we focused exclusively at building a processor architecture that was suitable for cloud providers, right? Those who need to actually, cut up those resources and be able to, give them out to their customers in a very prescriptive and concise, measurable way, right? So what does that mean? Well, today, Ampere is the leader in rack efficiency, right? We have the highest density compute in the industry. So, and that comes through 2 families of processors that we have. One is the Ultra family. That was the first one that the first family of processors that we released. And that you can think of as, it's an Arm Neoverse 8.2 core, that in the family there's 2 lines, the Ultra and the Ultra Max. That Ultra processor has 80 cores with essentially a single thread per core. So we have no hyper-threading in any of our processors. We just decide to throw more cores at it. So we give you a fast data pipeline into the core, L2, L3 cache, right? Direct, super fast. We can give you consistency because those clock frequencies of those cores are pinned at 3 gigahertz, right? So what this does is it gives us a way to have a high-performant core, high core count, and the TDP, for those who aren't familiar, is the amount of electricity flowing through that socket, right? The TDP of that socket is 250 watts. So what that means is, for example, we are building a chip that competes directly with Intel Xeon Bergamo, like all the high-end processors coming out of AMD and Intel. But yet, for example, the Intel Xeon uses 500 watts of electricity per socket. And that's just for the CPU. With us, because we're an SoC, that includes all the other networking, storage, and I/O. And because of that, we can take those, the density of that. So we have the Ultra, think of it as an 80 core. Ultra Max, 128 core. So we remove some of that L2, L3 cache to create more die space to jam in more cores. And then with the Ampere 1 family of processors, which is the one we released last year, we achieve a core density of 192 cores. And we do that because we created our own intellectual property for cores. So that will be an Arm Neoverse 8.4 compliant core. However, it's Ampere IP that is inside of it. So, and with that, we can get greater performance because we can linearly scale the cores, right? We use, because of the sheer, like that TDP, how much electricity each socket draws, it allows us to have exponential cost savings in terms of the power and cooling of that resource. And because we can jam so many cores into the socket, it allows us to help you reclaim that real estate, because now the thermal characteristics of the platforms we're putting in your data center use less power, generate less heat, increase exponentially your core count, allowing you to rack more servers in those racks than you could previously, right? So, and that, like I was saying before, this is what those cores give you is predictable performance, right? They're all pinned at 3 gigahertz, so there's no fluctuations in core. There's no hyper-threading. So when you actually look at the frequency of the core while it's under load, it's going to be very consistent. So for people that need to predict and deliver performance, especially people providing virtualization, containerization infrastructure, we can ensure that you're going to get 3 gigahertz to the core. It's not going to be a jumpy 2. You're not going to have those noisy neighbor scenarios where you have when using hyperthreads, because you're getting a single core per thread. And because of the nature of the power consumption and all those other things, we believe we are the first sustainable chip company, because we can allow you to think about your power consumption and allow you to plan your data center capacity in a growth phase while conserving your real estate, right? So it's we focus on power efficiency, right? And we are literally the industry leaders in performance per watt, right? Or price per performance per watt. So, the whole point is, we want sustainable, predictable, scalable, and cost-effective processors, right? We need, we want to be able to have as many of those cores throughout, in the data center, and we want to give you a path forward so you can continue to grow and increase your core capacity. And the reality of it is, less power is more power. With the momentum behind AI, we all know that we need more electricity to power all that stuff, right? There's a reason that all the cloud providers are moving towards ARM-based processors. It's more cost-effective for their own operation, right? And it's literally going to be more cost-effective for everybody. So, our chips are, as I mentioned, are built for modern workloads, especially when you think about microservices, containerization. It allows us to give you physical cores instead of hyperthreads, right? We have a lot of them so we can cut them up, allowing you to have higher dense compute infrastructure, right? And specifically, we've decided about 4 years ago to focus on accelerating inference. So a lot of things you'll hear today in the ether about talking about actually running your AI workloads. That's the inference component of running, not the training. We can come in some cases at 18% the cost of doing that operation, right? Because we can do it without using a GPU. By definition, out of NVIDIA's mouth, about 2 years ago at Open Compute Summit, in their keynote, they talk about efficiency of inference on an NVIDIA GPU today is about 60% efficient. So from that perspective, when you're paying that volume, that amount of money for that part, you really want to get the maximum efficiency across it all the time, right? So you would ideally keep the most critical workloads that can utilize that on it. And from a cost perspective, when you're thinking about GPU instances in terms of bare metal and clouds, sometimes the cost of that is about $24,000 a day. So, from a reality perspective, if you can run your AI workloads and inferencing workloads without the use of a GPU, there's a significant savings that can be had from an operational standpoint. So now, what types of platforms does Ampere work with? So as I said, when we first started out, we worked exclusively with the cloud providers, right? We were the first ARM servers in every cloud but Amazon, okay? Because they built Graviton before Ampere existed. However, over the course of the last 3 years, we've had to grow in other areas of the market, and this is one of the phenomenal systems that we've had a lot of momentum around recently. This is a System 76 Theo Astra, and essentially this is a workstation that's been developed and heavily used in the development of autonomous driving. Okay. So this you might have seen in going around some of the trade shows, if you've seen any of the talks that the RGS guys are doing. This is a next computing flyaway kit, right? So when we talk about edge, This is a TSA-approved carry-on. We can have 512 cores, right? And the Ampere processors, the Ultra family, can support 4 terabytes of RAM per socket. Today, these have the Ampere Ultras in it. They're about to shortly come out with another version that will have Ampere 1, and that will give you 8 terabytes of RAM per socket and dramatically increase the core count as well. So if you think about a use case like this, when we talk about telco edge, all those things, you can take this, roll it into an area that needs a radio access network, and you can bring it in and implement it instantly and have the compute power to be able to power it. Or think about in other scenarios, for tactical cyber edge and those sorts of environments, you have a complete cloud in a box, essentially, right? So then, Ampere processors can be pretty much found in a majority of major ODMs and ODXs today. And from my perspective, one of the proudest moments I had while being here at Ampere is when HP released the first Ampere server on a ProLiant. And that also, at the same time, was the first enterprise server that shipped out of the box with open source firmware. So as an option that you could get directly from HP. So that's one of the things. Ampere has always been an open source first company. We don't have a custom compiler. All our upstream development is in GCC and all those things. And we have focused on delivering and having open source firmware alternatives as well as the standard alternatives to our platform vendors who are building solutions, right? So like I said, today you can go buy an off-the-shelf HP server that has an Ampere processor in it. You can get it from Supermicro, Foxconn, WeWin, ASRock Rack, and a bunch of others as well. So, if you guys want more information about Ampere, obviously, we can come talk to me after, and there's some information here in the deck that you can come and look at later. So at this point, I'll turn it over to Alessandro to start filling us in on SUSE Virtualization and give us the show.
Thanks, Peter. I'm sorry if you've been through these slides before. Not everyone may have. If you were in our previous session, then there's a few that are there too. Yes, a little repetitive, but I promise the demo is unique. Okay? So if we talk about SUSE Virtualization, let's just recap very quickly. It's 100% open source software that reduces the reliance on boutique-specific hardware, right? Support different architectures, different vendors. And it helps you bridge the gap between cloud native and virtual machines, and it's ready. Right? It's opinionated, it comes with software-defined storage, networking stack, everything you need so that once you install it from an ISO, you're ready to go. And the value of SUSE Virtualization, as we've said, is the operational simplicity because you have a container platform and a virtual machine platform in one, in which they work in a cohesive way. That means it's built for that purpose, right? It's not an afterthought that you started putting things together just so that you could sell something. Right? The virtualization platform is built for containers, for Kubernetes virtual machines, and your traditional virtual machines. That makes it future-proof for IT infrastructure because it's very cloud-friendly, cloud-native friendly, and also for your current legacy or current virtual machines. Avoiding vendor lock-in is 100% open source software. Other partners and competitors ship very similar solutions, which provide the ability in the enterprise that when you embrace this technology, you have options. You can switch without creating this massive technical debt, just like you do today with Linux vendors. So what are the classic use cases where we would use SUSE Virtualization? Number one is to run containers on the bare metal, right? It is built up on a Kubernetes environment, a Kubernetes cluster. So naturally, if you have a high transactional or very high throughput, low latency workload that you need to deploy, I think you should deploy in a bare metal cluster. Then the second use case is to run traditional virtual machines. Okay, so just like your Windows, your Linux, your different distributions, et cetera, right? And then there's the purpose of hosting containers on isolated VMs. Yes, those are your downstream Rancher clusters. Rancher downstream clusters, there's a benefit on running on SUSE Virtualization because there are 3 key components. Number 1 is a load balancing service that's provided. Then the CSI pass-through. That means you can consume the underlying storage from the bare metal cluster so that your virtualized Kubernetes clusters don't need yet another software-defined storage or another storage layer, right? And we provide an isolation for those volumes that your different clusters are requesting. And the third one is the topology awareness. When we're placing pods, virtual machines, and whether those are in the isolated virtualization cluster or in the bare metal, the topology awareness allows us to spread out those resources for maximum availability, right? So there's some rack awareness or room awareness that allows for that. Then there is, of course, all of them, right? You can run containers in the metal, you can run traditional virtual machines, and you can deploy isolated or independent Kubernetes clusters on top of the platform. That allows us to assess a migration of, we don't have to migrate everything. We don't have to deploy everything in SUSE Virtualization. We can start easy, right? Like we did when we were all on bare metal, and then we started transitioning into virtual machines. Let's see how this works. What about the performance? What about this? What about that, right? There's always naysayers and people that don't want change. So what we do is we enable. We enable so that you can move the virtual machine. Once you move the virtual machine, then you can assess, is this really a virtual machine or should this be a container, right? And once you make that decision, then you can keep it as a VM or it transitions into a container. What's the stack built from? It's SUSE Linux Micro or immutable version of SUSE Linux Enterprise Server. RKE2, which is our, of course, enterprise Kubernetes distribution. Then SUSE Storage is our software-defined storage. And then we utilize Multis for our networking stack, and as well as KubeVirt, which is how KVM and Kubernetes interact with each other. We put them together, and it builds our SUSE Virtualization. Of course, you need other components, a dashboard, a cloud provider interface, and a lot of little details that are underneath that the SUSE builds. Where does it make sense to run SUSE Virtualization? A colo environment, in a data center, at the edge, and then we can manage all these SUSE Rancher Prime clusters, whether those are in the cloud or on-prem or your metal, all through SUSE Rancher Prime. Right. So what are some of the things that we will support? Of course, there is our bare metal nodes that Peter just showed us. Then there's the operating system, the kernel, it's all these dependencies, their interconnection with SUSE storage and those components that in an HCI mode reside, of course, on the host itself. And then there's the RKE2 components, the Multis, the CNI, and then the KubeVirt components that allow us to create virtual machines and interact with the networks and the different components that the virtualization requires. When we move on further, we see also what was just announced, that is the third-party storage support, in which you can plug in from different vendors your current investments alongside the HCI mode of our virtualization platform. And you're presented with our dashboard that provides a simplified way of managing the virtualization platform. Right, so that is, of course, kind of your crawl walk. If you want to run, then you can do GitOps, you can deploy those virtual machines as defined by YAML, you can do Terraform, and you can do a lot more automation, of course, right? And
Yeah, I guess I'll do some
Yeah.
talk about this. So, one of the things that Alejandro and I have been working on is trying to help drive awareness about the support for Arm64 software in the SUSE Rancher stacks, right? And there's been a lot of phenomenal work done by the SUSE team over the course of the last couple of years to help bring to fruition, a fully GA'd platform that will exist that can run entirely on an Ampere-based server. And as Alejandro said earlier, that's both on the cloud, either in a cloud instance in one of your major cloud providers today, as a server that you can get from one of the server vendors that build and supply platforms with Ampere chips in it, or at the edge, right? And you saw some of the edge devices that we have available. So, there's full ARM support for SUSE Linux Enterprise Server, for SUSE Linux Micro, for SLE Micro. For the multi-Linux manager, they'll support, traditional and client deployments on ARM64. So from that perspective, you have your core operating system components covered on an Ampere platform with, L1 through 3 support coming from SUSE. And then we go up the stack, right? K3S has been supported on ARM for quite a while. RKE2 is also now supported, and I believe G8 on ARM64, so that gives us, that extra, FIP certified Kubernetes deployment that will also, that you can now run on your ARM-based platform, right? Rancher Manager is currently experimental. However, I believe that's going to be GA'd hopefully shortly soon. And then Harvester, SUSE Virtualization is supposed to be GA'd within this quarter. I believe it's this or next quarter. So by the end of this year, or hopefully by Q3, we'll be able to have a full supported stack, commercially supported stack from SUSE that can run on an Ampere-based platform. And obviously, SUSE Storage, SUSE Security, and SUSE OS Management also are currently supported on Ampere platforms.
Yeah, so it's heavily supported across our portfolio. Why are we having a SUSE virtualization session when it's tech preview? Well, it's because it's impending, right? It's any moment with a future release, although we cannot say it is because it hasn't happened. Wink, wink. Yeah.
Yep. If I can add one thing, like as Alejandro is going to go through this demo, the compelling thing that most people don't realize is just the sheer core density that we can achieve. So if you can imagine in 3 nodes, and we can get a significant amount of cores, right? So when you start thinking about the amount of workloads that you can consolidate into a smaller footprint, and if you think about your physical data center footprint, it gives you, like I said, additional room to grow. And because of the way that sort of the SUSE stack is built, if you can imagine, that gives us an easy way to go linearly scalable, right? So n+1 kind of sideways very easily.
Right, so let's cover some of the SUSE virtualization roadmap. We've had plenty of things going on. It's heavily under development for a few items. We saw a lot of action with 1.4, with 1.5. One of the biggest, 2 of the biggest things, of course, one was just announced on the keynote. The third party is storage. And as we were just saying, as in roadmap, is ARM support for this. That's pretty much where we're talking right now. 1.5 is due for release the next few weeks. Can't provide exact dates, but it's March, mid-April, around that time, so you can really start testing. 1.5 release candidate 1 is already available and has most of the things that you'd look after that. Of course, we take at least, there's a month plus of QA before we even release that to the community. So 1.5 is imminent. And a lot of things also coming up in 1.6, a lot of in flux, so that we can focus on what we're doing. But you can see these are some of the items that are 1.6 in future that are coming. If you have any interest in a specific item, come talk to us, talk to our product management will take you to them so that we can focus as well if there's any point of interest.
And just one more thing to add, this is SUSE adding first-party support, right, for Arm64. And when you think of it from a parity perspective, we're looking at, equivalency from a feature perspective, function perspective. So whether you want to choose to do it on an x86 legacy platform or go to a more cloud-native ARM-based platform, you'll still have the same SUSE software, SUSE feature set, and software stack delivered, right?
Yeah.
So that's a big thing, right? Like equivalency is big.
Yeah. So for example, we 1.4 we supported CPU pinning, which has the ability to pin a core to the virtual machine, right? So that's not really sharing the cores that much. That of course works on Ampere and of course on the ARM platform. So like Peter said, it's feature parity as well. Full support with SUSE. Right. So let's go into a demo. The demo could be quite long, depending on how much you guys want to see. Then we'll go into questions. It is, of course, a live demo. So if anything goes wrong, just let me know.
Only me. So just to give a little background on the equipment that you'll be that'll be actually running in the background of the demo. Those are Mount Collins platforms from Ampere. They have I believe two Ampere Ultra platforms. So you get 160 cores per chassis and a 2-socket configuration. Okay. Now, one of the things to know about the Ampere sockets is in the family of processor, they are socket compatible, meaning the experience that you have working with that server and changing chips out and putting them in will be very similar, if not identical, to those that you had when managing traditional servers. We are building servers. Your experience of using servers are always going to be pretty similar, right? The only difference is ours use half the electricity and deliver way more compute power and storage and RAM and all the other things that you actually need to compute. So.
Thanks. So yeah, as you can see, this is Rancher, of course. Within Rancher, we can immediately see our SUSE Virtualization cluster. You can absolutely already tell the difference in CPU availability compared to the rest of the clusters. There's different parts of our demo in which we focus on just a virtual machine and then deploying a cluster. Deploying a cluster takes a little bit longer, so we'll jump on that at first. So we're going to head and click Create, and we're going to provision. So I had to change the zoom so that you guys can see a little better, so that it doesn't look as pretty, but we'll work on that here. I'm going to choose Harvester SUSE Virtualization as the provider, and then I'm going to deploy this cluster on my Ampere cluster, and we're going to call it SUSECon demo. This is an all-in-one pool because we're going to create a 3-node etcd control plane and worker nodes. We're not going to use 2. We're going to use 32 CPUs and 64 gig of RAM. Then we're going to choose the default namespace. We could do this demo with any operating system. Usually, doing a demo with SLES is just too easy because it shows, we can do our stuff with us. But it is our conference, so let's go ahead and do that. And I'll choose an image of SLES 15 SB6. And for now, we don't really care about the hard drive, so we'll leave it like that. So we also create the spec of our VM. I'm going to choose it to be attached to VLAN 1 on the VLAN 1 network. Then I can click Show Advanced. Show Advanced allows me to then provide further details into how this VM is being created. And what's going to do then, it's going to inject with a cloud config my user. It's going to allow me as a sudoer, set a password, a very secure password, don't tell anyone. Enable SSH password authentication, register me with SUSE SEC. It's going to disable IPv6 because I don't use that in my lab. then it's going to install some packages that I need for my VM. Moving on from that, of course, by the way, if I had any GPUs in the system, I could attach them right here. They would be scheduled with the VMs that are being created. As we scroll down, we can choose the Kubernetes version that we want to specify and the cloud provider. It's important to choose the Harvester cloud provider because it provides us with the three things we had already mentioned, right? Load balancing service, CSI pass-through, topology awareness. If you don't choose that, then there's no really integration between the hypervisor and the virtualized cluster that we were deploying. As you can see, this is exactly the same experience as if you were creating, make sure I did everything, there's a name, and any other architecture. The only difference is that we put a little bit more cores in that. As that SUSE Rancher Prime cluster is being deployed, let's jump on the SUSE Virtualization dashboard for this cluster. Once we click here in our Ampere cluster link, we can see some basic information about the amount of hosts that are in this cluster, the virtual machines, some capacity planning information with regards to how much is being utilized, reserved, how much memory is in use. As we can see, we already have some virtual machines being spun up. But meanwhile, I'll show you just some of that information. So there's monitoring embedded in the system too. You can enable or disable it based on what you would like to use for that. And you get information with regards to CPU utilization, memory, IOPS, network, etc. You can also see cluster metrics, which are specific to the bare metal, the hypervisor-specific metrics, and the virtual machine metrics, right? So these are two completely different items. If we click on the Grafana link, there's way more components that you can look after. And there's, of course, all your different dashboards. So if we have to look at the different graphs, it's probably in the hundreds. Of course, we're not going to show that in the SUSE Virtualization dashboard because it would just clutter the UI. We definitely don't want that. So I mentioned these VMs are now being provisioned. Those are the VMs for our SUSECon demo RK2 cluster. Well, again, those are being provisioned. I can create just traditional VMs. So let's go ahead and do this. Just give it a name. But you know what? Let's actually create multiple instances. And I want 3 instances with 8 CPUs and 4 gig of RAM. Then I can inject my SSH key so I can access it easily. This time, we probably can choose another operating system. Why not? Let's choose an Ubuntu image, giving it a 20 gig disk, while we also configure our VLAN 1 network. There's additional options with regards to node scheduling. If I would like these VMs to be pinned to a specific host, I could do that. If I like them to have the scheduler plays the VM based on affinity, anti-affinity labels, and CPU memory, pretty much the scheduler choice based on resource utilization, we can do that. Or we can, of course, just set virtual machine selections where you can schedule those VMs on a specific host. For example, if there's a VM that has a hardware that I would like to do PCI pass-through, and I really want that to be on a specific host, then we can pretty much pin it there, or we can just label that VM and make sure that it goes into a specific subset of hosts that we want it to. Okay. Then there is instance labels that we can add for things like that, and the advanced options. The advanced options is just as equal as we were showing before. I'll use a generic one because it's non-specific to an operating system, and it does the same thing, right? Creates my user, sudo, password, disabling things, installing packages, injecting SSH keys, doing all that beautiful automation. We could do CPU pinning so that then we are assigning cores to those virtual machines based on the number that we assigned before. TPM, EFI mode, and secure boot as well. So those are all additional settings that we have. Based on the cloud config, it's going to provide the host name that we set here to the VM. If we wanted to, we could set a specific host name. If we wanted to do that rather than use the same of the virtual machine, we could also set a reserved memory, a run strategy, and a migrate strategy. What are those last two? The run strategy is if that VM was running and there's a host failure, what should we do? Do we just never mind? Or do we do fault tolerance, which means that VM should be scheduled on another host as soon as possible based on the affinity, anti-affinity, and placement rules. Okay? That is a run strategy of rerun on failure. Then there is our migrate strategy, which when we're doing an upgrade or doing a migration of this, the host, we can choose that whether we really want to do live migrations of those VMs, or do we just want to shut those VMs down because maybe they're dev VMs or things that we don't want to be moving around on an upgrade, and then we can more quickly perform upgrades on SUSE Virtualization. So there's, of course, different use cases, but you have more control of when we talk about automation, what is the strategy for that VM? Anyway, let's move on. We have SUSECon demo VM. We're creating 3 multiple instances. We'll go ahead and click create. And then that was pretty simple. It's creating 3 of my 3 of those virtual machines on our cluster. What's it going to do naturally? Now that we've selected that we want 3 VMs, and if we don't pass any additional affinity things, affinity settings, well, it recognized that we're creating 3 VMs. We have 3 hosts. Well, why not? Let's make sure that we spin them up on different systems. So we created 1 on 1, 1 on 2, 1 on 3. And if we go, for example, on this one and click on virtual machine scheduling, it auto-created a preferred anti-affinity rule between its other VMs that are named equally. Okay? So there was an immediate anti-affinity setting there too. Let's go ahead and see the first thing as we can do is open a serial console. When we have a serial console, it's exactly what you get, a serial console. So that you can copy paste, and you can also see all the ugly things that your operating system is spitting on you, right? That's just normal. That is your serial console. As you can tell, the host name has been set as part of the cloud config injection. We didn't do that, right? It was just the name of the virtual machine. That is the serial console access. If we go here in the web VNC, then we get that pretty option that we were looking for, which is just, again, our VNC console, our graphical console. Right? Let's go back to what we did first, which was create the SUSECon demo. If we go here into our barn and click on the demo and the provisioning log, we can see that is about done with the cluster deployment. We're at the 8-minute mark. We already have one of those systems that is fully ready. So once these other components on the additional cluster nodes are done, we'll have a Kubernetes cluster with, like I said, a storage, a load balancing capability, so you can do a service type load balancer, and full topology awareness as well.
If I could just add one thing.
Of course.
ARM has spent a lot of time, right, building a certification process to ensure that the user experience of ARM-based server technology, virtual machine technology adheres to what you're used to, right? So a lot of that stuff has been put into play to ensure that the user experience that you're going to have when using an Ampere processor, Ampere server, or an Ampere-powered virtual machine, it's going to be pretty much identical to whatever you have. The experience of using Linux and other operating systems on that platform are going to adhere to the user experience that you're used to, and from x86 based platforms, right? So you can pixie boot, you can do all those same things in the same way that you're used to. The only difference is the software that you're using will be a different architecture, right?
Great. So now, having said that, pretty boring demo, right? I mean, that's the whole point. It's just that what you were doing on X, you can do here as well. And it's just the exact same experience, just with more cores, lower power consumption. That's our Kubernetes cluster right there. And there's a SUSECon demo cluster. And we can then just do whatever we would, right? We can then go into our apps and our charts and deploy our different applications. So how long did that take? How long did that take to provision? Sorry for all the clicking. There we go. 11 minutes. We were pretty much done. Okay. So we provisioned the Kubernetes cluster with full CSI integration and the cloud provider integration with Harvester. We deployed 3 virtual machines. We did SSH key injection, package installation. We did some automation for those VMs. Pretty boring. It just worked. And we pretty much can do anything that you can with X on ARM, right? Again, it's tech preview in the roadmap, and we cannot expand on the date, but as you can see it right now, it's what it is. If you look at what this entails, is that there's RK2, there was Longhorn, talking upstream here, right? RKE, Longhorn, Linux. There's additional components, kuberts. There's all the different things that are needed, all of course on ARM. Okay. So I don't know if there's anything else you'd like to add, or should we open it?
I say we got time.
Well, actually, we only have 5 minutes, so I thought we had a lot of time. But any questions? Whether that is specific to Ampere platform, or SUSE Virtualization, or anything else we've said.
I'll just make a comment on what you said. It just works, right? Like, that's one of the things that we've been, and I know my 6 years here at Ampere have been focused on, is I want to ensure that you never know it's an Ampere server underneath you, right? Like that, you're just like, oh, I have this great compute platform, it's wicked stable, I can manage it the way that I'm used to, and oh, crap, it uses half the electricity, right? Like, given the direction, I think just in the US next year, we're talking 30% increase in data center infrastructure. That's a lot of power, right? If you look at the alternatives, right, if we're going to stay with x86, we need to move to liquid cooling as soon as possible, right? Because that's the only way we're going to get the density in the data center, right? And I don't know how much you folks know about full immersion liquid cooling, but it frightens the hell out of me from the standpoint that if you look at the direction of contamination in this planet with plastics and PFAS chemicals, from my understanding, best case scenario for liquid cooling is that it has about 18 PFAS chemicals. Worst case, you're over 200, right? As you heard in the keynote yesterday, you're going to have chemical engineers helping you determine the, the chemicals you're going to use to immerse your servers in. And those servers were not designed to be immersed because, once again, we primarily live in a technological ecosystem, right, that relies on legacy technologies that get repurposed, like your GPUs. That's a graphics processing unit, right? It's not an AI accelerator, right? So those things are currently being repurposed, and Ampere decided to take the approach about changing the way we're doing it to ensure that we have a path to go forward that's more efficient in terms of our data center computing, the real estate that we're using, the physical assets and resources that we're using, right, to get the most value out of that to deliver to the, our customers and SUSE's customers and anybody who's using an Ampere platform.
Yeah. No. Well, so if one more time, if there's any questions. All right. Then thank you very much for coming. And if there's anything, let us know. Thank you.